The second topic we're going to cover in Chapter 2 is the basic statistical descriptions of data, and we're going to look at those. So we're going to cover measurements for central tendency to see what's the average, the main message the data want to send us. There are sets of measurements, mode, median, mean, mid-range, that can describe the central tendency of the data. What are the most commonly occurred value in this data set, for example? We're going to also look at the measurements that describe how widely the data values are dispersed. So dispersion measures of the data set are of include range, quartiles, interquartile range, 5-number summary box plots, variance and standard deviation. We're also going to look at the graphs that can actually visualize those summaries and distributions intuitively for us. So why do we need to learn all of that? We need to learn those because we need to first get to know our data before we can perform any data mining tasks. We have to have an overall idea how data is distributed, what are the tendencies, are data skewed or normally distributed, before we can select the reasonable mining methods. And also by looking at the data going to reveal to us some interesting things that's unexpected. Oftentimes, this is the stage where you're looking at the data, you actually come up with different hypotheses that you want to test based on what the data shows. So getting to know your data is a very critical step in any data mining tasks. Those things, I think some of you probably already know all of this because those are pretty basic. I think any statistics class should cover all of it. So if you already have all those, looking at those terms, those are all look familiar to you, I really don't think you need to go through this video. You can just quickly run through the slides. Oh, I'm sorry. For a student who's new to statistics, never took any statistics class, this would be a good introduction. Okay, so the first set of measurements we're going to look at are the central tendency measurements, mean, also called average. I think we have used it in our everyday life fairly often. So this formula help you to calculate sample means, and this one is for population. When you actually know the population, a lot of times we don't actually know the entire population. We only sampled certain observations from the population. So this is more likely the one that we use more often. However, when you look at these two formulas, they're exactly the same. Only the n is the sample, and this n is the population. So we sum up all the individual values and then divide it by the number of the observations that we have. That gave us the average. Also, in machine learning, a very commonly used arithmetic mean is weighted arithmetic mean, because a lot of times our attributes may not have equal weight. In order to create a mean value for this observation, we need to look at each of the attributes, but each of the attributes have different weight, so we have to actually apply the weight to the value of each of the attributes and then compute a weighted arithmetic mean. I have one slide here to illustrate this idea. See, in this class, if we have 3 exercises students do, and I have different weight. Exercise 1 is the most challenging, so I weighted more. I gave it weight of 0.8. Exercise 2 and 3 are not only brief, I mean, it doesn't take much time, it doesn't take much of a thinking either. So I gave it a smaller weight of 0.1, 0.1. And then 2 students did this 3 exercise, and they scored differently on those different exercises. If we took a simple mean, disregard all the weights, we just took those 3 numbers, added up, divided by 3, we get the mean score. We can see this mean score tells us student 2 performed better than student 1, which is misleading because I put weight on this exercise, meaning this exercise means more to me. This exercise is going to tell better, provide a more accurate estimate of student performance. And this student did 100 on this hard task, and we only give a mean score of 66. So this is a misleading score, and we can use the weighted, taking the weights into account. Apply the formula that we just look at it. So the formula says to multiply every value with the weight, sum each individual values up and divided by the sum of the weight. And this is how we're going to do it. So here, our formula is to apply the weight to every value. We time the value with the weight, took the product of the two, and add every values for each of the exercise together. And then we divide it by the sum of the weight. So sum of the weight is 0.8 plus 0.1 plus 0.1. So that gave us the weighted mean score of 90 for student 1 and a weighted mean score of 60 for student 2. These numbers, those 2 values, represent the true performance of the student on those 3 weighted exercises. So this is why when we do machine learning and data mining, we sometimes weigh different attributes differently. This requires domain knowledge. Nobody going to tell you how much to weigh them. You will have to figure that out either through your experience or by consulting domain expert, which of the attributes contributes to the answer the most. So we can give them more weight. This, as I suggested, weighted arithmetic mean is used widely in all machine learning and data mining tasks. We will come back to this next week and the week after. A lot of occasions you're going to see this being applied. Trimmed mean is used when you actually have outliers, extreme values. In practice, this is also used in score competition. I don't know if you look at finger skating competition. Every time there's like 10 judges, and they always drop the minimum score and the maximum score and average the rest to get the mean score for a contestant. This is a chopping extreme value example. It's trimmed mean, that we remove the lowest and the greatest as if they're outliers, and we average the rest to get the mean. Media is another way to measure the central tendency, because sometimes our data are skewed. The mean may not represent provide a true representation of the central C of the data. So we would use median. So median, if you sort this a vector of values in order, median is the value that occurs in the middle of that sorted value. So if you have odd number of ordered value, then the median is exactly the value of the the data that's in the middle of this sorted vector. If you have even a number of values, then you will have two values sit at the middle of this range, of this order. So you will take the average of the middle two values to find the median. A lot of times the data, the raw data may not be provided to you, but the data has been discretized and give you the ranges, the grouped data. For example, here we have a group of data that we don't know each individual's age, but we know between age 1 and 5 we have 200 individuals. Between age 6 to 15 we have 450 individuals. When you have such data, there is a way for you to estimate the median using this formula. So we will get to this later. Mode mode is the value that occurred most frequently in your data vector. Okay, so for example, just using the age in my son's class, maybe majority of the student going to be 10 years old. So that 10 is a very representative value for this group of student. So value that occur most frequently in the data is called mode. It's also a central tendency measurement. Sometimes the data may have multiple values that occurred at the same frequency. For example, this group of students, maybe 5 of them are 10 years old and other 5 are 11 years old. And then this data is called bimodal because they have two values that occur with same frequency. The most frequently occurred value are not just one value, but multiple values. So in those cases, you will have bimodal, trimodal value. But if all the values occur at the same time, you have 10 values, every value is 1, then we call this data set no model. There is not a value that occurs more frequently than others. Okay. There is an empirical relationship between mean, model, and median if your data is not heavily skewed. So this formula is useful because mode and median are hard to find. Median especially are hard to find. Mode and mean are easier to find. So if you know mean and median, mean and mode, you actually can estimate median. That will make it will make median computational feasible. As median is when you have a very large data set, sorting everything out and then get the median is costly. That you can use once you know any of those two, then you can estimate the third one. So now we can go back and look at this formula that we touched upon. Sometimes, well, in general, median is more costly to compute than mean, and mode. And also the challenge is also when you have data being discretized, well, you will see throughout the semester, discretizing, making data into groups, breaking up data into groups is a very common practice in machine learning and data mining. Therefore, it's highly possible that sometimes you have to estimate the median using interpolation on grouped data. So in this case, we have age we know the frequency of each number of observations or number of individuals that falling into those age groups. Then how do we estimate this? So the book gave you a big formula, looks like this. And the elements that required to compute, to estimate this median is the big N. Big N is the total number of observations. Adding those up, you will get this number. This is your total observations. And L1 is the starting range of the starting number of the range that could hold the median. Okay, so we know the total number of observation is this. Then we know, because the median is the middle value, right? So we know that if we sort this thing in the order already, then our median going to be the 1597th observation. So looking at those numbers, those are only 950, adding those up. Therefore, we know that our median must fall within this range, right? So therefore, we take 21. This the starting value of the range that holding the median that we're going to estimate. And then this frequency is everything that occurred before. All the observations has a value that's lower than 21. So we're adding this up, these three values together, we have 950. Okay. The frequency of median is the count, the observations in that median group, that in the group that holds the median. So we have 1500. And the width that's needed here is 30. That's the range of that group holds the median value. Okay, so putting this together, you can estimate the median. This, I don't know if that looking at this alone, does that make logic sense to you? You see why this number has to be divided and subtracted and multiplied to get the median? If you don't, then I have illustrated, I pictured it. I draw the picture to show why this formula works. Okay, why this formula works? Because we know, so the lower part is the age in my graph. The upper part is the count, frequency, how many individuals we have falling with each range. So given what we know that the age was from 1 years old to 110 years old, we know we have total of 3,194 observations. We know that from age 1 to age 21, we have 950. And we know our median has to fall at this position. So here from age 1 to the median, to the individual that has the median value, there has to be 1,597 person ahead in front of it, or younger than this person. And we know the range that holds our median is here from 21 to 51, and 1,500 is the total number of people that we have in this range. Okay, so after I depict this, you will see this formula is basically L1 is 21, to half of the N is this much, and the frequency before here, before the age 21 is 950, and this is here. So what you see that we're doing all those to find what this x is. This x is 1,597 minus 75 in terms of how many people are here. How many, and then we know that if the individuals within this range are uniformly distributed, then we know the proportion of of this x to to 150, 1500 has to be the same as the proportion of this age difference that we're trying to find to 30. Okay, so this is how we can use this formula to find this x, and adding x, the age difference to the starting range for this mid group, or the group that holding the median, going to give us the median age that we are looking for. Okay. So that answered our question on why this formula makes sense. It's fairly, once you depicted the picture, it's fairly straightforward. Next, we're going to we talk about the central tendencies, right? We talk about when we have mean, why do we need median? Because mean and median mode may not always be the same thing. They will be the same only when your data is symmetric, follow a normal distribution. When your data are either positively skewed, when you have a long tail towards the positive direction of the coordination, or when your data is negatively skewed, if you plot it and you see a shape like this, that you have a very long tail towards the negative direction of your coordinates, then you then the mode median and mean may not be the same. In positive skewed case, your mode is always smaller than median, and the mean could be larger than median. When you have data negatively skewed, your mode is always larger than median, and the mean could be smaller than median. When you have skewed data, you wanted to not only look at the median, not only the mean, you want to look at the mode and the median to get a better understanding of where the data are centralized. So now we look at those graphs, we can see that one number cannot really give us the whole picture of how data is distributed. Therefore, we also need dispersion measurements to tell us how what the whole distribution look like. So we will have a whole set of measures. This include your typical and the one that you might already familiar, variance and standard deviation. But also there is other set of other measures that actually can characterize the data distribution as well. Those are range, quartiles, outliers, and box plots. So range is the difference between the largest and the smallest value in a data set. And we also define mid-range as the average of the largest and the smallest value in the data set. It's the average of the two values, not and the range is the difference between these two values. And quantiles are the points taken at regular interval of a data distribution. When you see this, you know this quantiles applies to interval data, because every interval has to be defined for quantile to be meaningfully applied. So quantile, there are different quantiles can be taken at different intervals. Typically, there's two typical ways of choosing those intervals. One is divide the data to 4 equal sized, so every portion has same number of observation, divide those the data into 4 intervals. So those are the quartile measures, so represented by Q1, Q2, Q3. Those 3 points would divide a data distribution into 4 portions, right? And the percentile is actually taking those points at every percentage. So as you can intuitively see that Q1 corresponds to 25th percentile, Q2 corresponds to the median, which is 50th percentile, and 70th Q3 corresponds to 75th percentile. So in each every, although we're taking one quantiles is marked by the points defines a range, and that range covers the same number of observations. I'm sorry, this slide is jumpy. And then with those quartiles, we will be able to define interquartile range. This is a very important measurement because using this, it can tell us what the outliers might be. I think last week we mentioned noises and outliers. Noise are something that we definitely want to remove, but outliers could be something interesting to study. So in statistics, typically a value that's higher or lower than 1.5 times of the interquartile range above or below Q1 or Q2 are considered outliers. If all those concepts are brand new to you, at this time they may not make much sense to you. No worries. When we look at the box plots, they're going to make sense because when we visualize them, you will see, they make sense. So we also mentioned variance and standard deviation. Those standard statistical measures that's used widely. Very fundamental concepts in statistics. So the variance is computed using these two formulas. Again, this is the sample variance. This is the population variance. Their formulas are very similar. So the idea is you took the sum of the square of the difference between individual values and the mean. You sum them up and took the average. So this is how far apart every value to the mean. Okay, so therefore variance measures the dispersedness. If lots of data, if all those data points are very close to the mean, then this value is going to be very small, and then your variance is going to be small. If the data are very far away from your mean, then this difference is going to be large. After it's squared, it's even larger, and then you're going to have a variance that's big. Okay. From variance, we can derive standard deviation, which is basically the square root of the variance. So we want to take the square because there's positive and negative differences. Therefore, square remove those concerns. We just took the absolute, the positive values, measure the positive differences. So when you look at this, if square is meant to do that, then can't we just took the absolute difference between these two? We can, and that's a different measure, which is called mean absolute deviation, MAD. MAD is much simpler. You can see it, right? It just take the absolute difference and sum this up and divide it by the m. So so the difference between these two is when you have extreme outliers, MAD would be a better estimate of dispersiveness, because taking square will just to make the difference even bigger when you have extreme outliers.